Hello viewers, today we will discuss about polymers. The word polymer is derived from Greek words poly and mers. Poly means many and mers means units. So, we may say that when many units combine together through covalent bond, then the formation of megamolecules or macromolecules takes place. These molecules are known as polymers. Polymers are extensively used in human life as in the area of plastics, children's toys, fibers, elastomers, synthetic rubbers, etc. Today, in this session, we will discuss about the polymers and polymerization, addition or chain growth polymerization. These are the mechanism of polymerization, free radical vinyl polymerization, ionic vinyl polymerization, Ziegler-Natta polymerization, vinyl polymerization and condensation or step growth polymerizations. So, first we must have to know that what are polymers. These are obtained by intermolecular combinations of the same or different types of similar molecules. These are linear or branched in nature. In this diagram, we are seeing that in center this is CH2 and CH2. These are the repeated units and that is an example of polyethylene. And in this structure, we are seeing that the repeating unit is CH2 CHCl, that is the vinyl chloride, and when more than one repeating units are combined together, then the formation of polyvinyl chloride takes place. In this structure, we are seeing that CH2 CHCH3 is the repeating unit and the formation of polypropylene takes place when these repeating units are more than one in number. So, a polymer is a large molecule made by repeating units of small molecules called monomers linking together. The formation of polymers can be understood by this reaction. This is the monomer unit, that is n number of monomers, and by the polymerization these are converted into polymers, and this is the covalent bond in a regular manner. This can be understood easily by this diagram. These are the monomer units of ethylene molecules and these are forming polyethylene, means more than one unit when combined together, then we have the chain like structure in linear manner, that is known as polyethylene. So, polymer formation takes place by the process polymerization, and it is a process of chemical combination of a large number of simple molecules of certain types. These are known as monomers repeatedly in a regular manner to form a giant molecule. These are known as polymers. So, now we will discuss the range of polymers. In terms of polymers form or function, these are classified as additives, fillers, absorbents, extrudants, moldings, containers, foams, sealants, adhesives, photoresists, paints, membranes, film, rope, textile, monofilaments and fibers. So, we may say that we are living in a polymer world. Most polymers are hydrocarbons, that is made up by hydrogen and carbon. These are of following types, that is saturated hydrocarbons, each carbon bonded to 4 other atoms, that is ethane, and unsaturated hydrocarbons. These are of further 2 types, that is double bonded as ethylene or ethene and triple bonded as acetylene or ethine. Here in this structure we can justify the saturated hydrocarbons and unsaturated hydrocarbons which are formed or forming polymers as, that is CH3 combining with CH3 by this covalent bond and the formation of ethane is going on. This is an example of ethylene having double bond, and this is an example of acetylene, it is triple bonded hydrocarbon. Now, we will discuss the synthesis of polymers. Polymers can be synthesized from different methods by using suitable monomers. These are of following types: chain growth or addition polymerization, step growth or condensation polymerization, catalytic polymerization. These types of different processes can be understood by this diagram. This is the polymerization process is basically of two types, that is addition polymerization, or we may say that chain growth polymerization, and another one is condensation polymerization or step growth polymerization. Now, addition polymerization is further of three types, that is free radical, ionic and catalytic. This ionic polymerization further of two types, that is cationic and anionic. Now, condensation polymerization is further of three types, that is polycondensation, ring opening polymerization and polyaddition. Now, the third type of addition polymerization is catalytic, which is further of three types, that is Ziegler-Natta catalyst, metallocene catalyst and chromium catalyst. These are the catalysts by which we can form different kind of polymers, which are known as addition polymers. Chain growth polymers, also known as addition polymers, these are made by chain reactions. In this process, the unsaturated monomers are converted into polymers of high molecular weight. It has to be noted that there is no liberation of any small molecule during addition polymerization. Example: polyethylene and polystyrene, means when the ethylene monomer units combine together, then the formation of single chain of polyethylene takes place, means no another molecule formation is going on in this polymerization process. It can be understood by this diagram. These are the styrene monomer units. This is one unit, second and third. When these monomer units combine together, then the formation of polystyrene, a chain growth polymer, takes place. Here we are seeing that this CH2CH C6H5 is the repeating unit of polystyrene, and another form is step growth polymers. These are also condensation polymers and are made up by combining two molecules by removing a small molecule as water or ammonia. So, we may say that in these polymers the formation of byproduct, or you may say the another product along with main polymer takes place. So, in this process the polymer must be made from monomers that contain more than one functional groups, and these functional groups may be amino group, carboxylic group, etc. It can be understood by this diagram. This is the monomer unit dimethyl terephthalate, and this is the another monomer unit, that is 1,2-ethane diol. These both monomer units are having two different kinds of functional groups, that is this one is RCOO CH3 and this one is ROH. When these both monomer units combine together by heating, then the formation of dacron, or we may say the polyethylene terephthalate takes place. This is a step growth polymer, and along with this repeating unit we have another molecule of methanol, that is CH3OH. So, it is an excellent example of step growth polymerization, and it proves that in this polymerization both functional groups are of different kinds. Types of addition polymerization. Addition polymerization takes place via three methods, that is free radical addition polymerization, cationic addition polymerization and anionic addition polymerization. Now, we will discuss free radical polymerization. In this polymerization, many low molecular weight alkenes undergo rapid polymerization when treated with small amounts of a radical initiator, that is the polymerization of ethylene. The whole process proceeds under three steps, that is initiation, propagation and termination. In initiation step, the formation of free radical takes place. Here it is a molecule, that is RR, bonded by covalent bond, or you may say the bonded by sharing the electrons. In the formation of radical, the sharing of electrons, or we may say the bonding, breaks down and the formation of free radical takes place. This symbol represents the formation of free radical. Now, this free radicals combined with this ethylene molecule, and this ethylene molecule, here we are seeing that this is the covalent bond, it shared electron over it, and we have the formation of free radical in this form. The next step is propagation. In this step, the growth of chain, or you may say the growth of free radical takes place. This is the free radical formed in initiation step combined with another molecule of ethylene, and here the same procedure repeated, and we get the enlarged free radical chain. Here we are seeing the CH2, 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 means monomer units are repeating over here, and further this free radical reacts with another molecule of ethylene and chain growth is going on in forward direction. Third step is termination. In this step, the formation of polymer takes place and the free radical combine together by covalent bond, and it can be determined by this diagram. Here we are seeing that two free radicals are present and formation of polymer is going on through this covalent bond, and this molecular mass, or you may say that higher molecular mass, can be controlled by the chain transfer, and this chain transfer can be understood by this diagram, that is the free radicals combining together and the formation of two different polymers are going on. The molecular weight of the polymer can be controlled by a process known as chain transfer. Chain growth polymerization of mono-substituted ethylene exhibits a marked preference of head to tail addition, which can be understood by this diagram. This is a monomer unit having tail and head. Head contains the functional groups. So, this is the combination of head to tail, that is CHZ combining with this CH2, that is tail, and this one is head. Here this is CH2 CHZ and CH2 CHZ. So, we may say that in this structure head to head combination is going on, and in this third type of combination CHZ, CH2, CH2, CHZ. So, here we are seeing that these are the tails of two monomer units and combining together, and the formation of tail to tail is going on. Head to tail addition of a substituted ethylene results in a polymer in which every other carbon bears a substituent, which can be understood by this equation. This is the monomer unit, that is CH2 CHCl, it is head and this one is tail. Here we may say that head to tail combination is going on in this whole chain, and this is the example of polyvinyl chloride. Here the monomer unit is vinyl chloride. This is the second type of addition polymerization, that is ionic polymerization. Ionic polymerization is more complex than free radical polymerization. The type of ionic polymerization depends on the nature of the substituent, that is R, on the vinyl monomer. It is further of two types, that is cationic and anionic. In cationic, initiation is therefore usually limited to the polymerization of monomers where the R group is electron donating. So, we may say that in cationic initiation the R group is electron donating, and in anionic initiation the R group is electron withdrawing. So, formation of cation and anion can be understood by this diagram. This is the cationic change and this one is anionic change. Here we are seeing that R is electron donating group and here R is electron withdrawing group. So, anionic polymerization involves the polymerization of monomers that have strong electron withdrawing groups, that is acrylonitrile, vinyl chloride, methyl methacrylate, styrene, etc. If the monomer has only a weak electron withdrawing group, then a strong base initiator is required, that is butyl lithium. For strong electron withdrawing groups, only a weak base initiator is required, that is a Grignard reagent. Initiation mechanism requires the direct transfer of an electron from the donor to the monomer in order to form a radical anion. This can be achieved by using an alkali metal shown in this diagram. This sodium is an alkali metal, is transferring its electron to this compound, and here we are seeing that is the free electron, and here the charge is generating. Anionic polymerization further takes place by 3 steps, that is initiation, starting, propagation, that is growth, and termination means completion of polymerization. So, initiation is the rate determining step in which the formation of anion takes place. Here this is NH2 is releasing its electron towards this one CH2 CH, and we may say that it is the styrene compound, and combining of NH2 is going on through this sharing of electron, and the formation of anion is going on. Now, we will discuss about the propagation, or we may say that the chain growth step. In this, anionic monomer unit is further combining with another styrene unit, and we are getting the chain in this form along with this anion. Now, the third step, that is termination. This is non-terminated chains are called living polymers. It can be understood by this diagram. Here we are seeing that this is the styrene unit, or we may say that these are the monomer unit. When combined with NH3, then this anion moves, or you may say that this ion moves towards this NH3, and we have this structure along with this NH2 ion. The chains remain active until they are killed, that is vinyl chloride, styrene, etc. Now, we will discuss cationic polymerization, that is also a form of addition polymerization. It is further takes place through 3 steps, that is initiation, propagation, and termination. In initiation, the formation of cation takes place, which are shown in this figure, that this is the monomer unit, and this is the cation, and this one is anion, that is reversible reaction. That is the transition stage where cation formation is going on, and finally, this is the monomer unit, and here we are seeing that cation and anion are present over here. This is the equilibrium diagram. In this diagram, we are seeing that movement of cation is going on, and finally, it joined to carbon. In propagation, chain growth takes place through the repeated addition of a monomer in a head to tail manner to the ion with retention of the ionic character, which is shown in this figure. Here we are seeing that the chain growth is going on, and finally, we are getting the polymer. This is the third step, that is termination. Termination of cationic polymerization reactions are less well defined than in free radical processes. 2 possibilities exist as unimolecular rearrangement of the ion pair, which is shown in this diagram, that is polymer and that is the ion. It is the unimolecular rearrangement of the ion pair, and we are getting this structure. In this, hydrogen abstraction occurs from the growing chain to regenerate the catalyst co-catalyst complex. Covalent combination of the active center with the catalyst co-catalyst complex fragment may occur, giving 2 inactive species. The kinetic chain is terminated and the initiator complex is reduced, a more effective route to reaction termination. Another type is bimolecular transfer reaction with the monomer. It can be explained by this diagram. Here, this is the polymer having this cationic generation and combining with another molecule and finally converting in polymer. reformation of the monomer initiator complex, ensuring that the kinetic chain is non-terminated by the reaction. Now, we will discuss the Ziegler-Natta catalyst. Ziegler-Natta catalyst commonly used in the polymerization industry to form different kind of polymers, that is polyethylene, polyvinyl chloride, polypropylene, etc. Here we are taking the example of polyethylene by this diagram, that is the monomer unit acetylene comes under unsaturated hydrocarbons. It is having triple bonds, and by using Ziegler-Natta catalyst it is converting in polyacetylene. It is long unbranched polymer and can be prepared by using an aluminum titanium initiator, that is known as Ziegler-Natta catalyst, as polyacetylene and polypropylene, etc. Polypropylene showing examples of isotactic and syntactic tacticity. This is the arrangements of groups on this chain of polypropylene polymer. Here we are seeing that CH3 groups are towards same plane, either these may be towards above the plane or below the plane. So, we may say that when these CH3 groups are locating towards same side, then this form is known as isotactic, and in this structure we are seeing that CH3, 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 location of these CH3 groups are towards above the plane and below the plane. So, this is the example of syntactic, or we may say that above and below the plane configuration. Now, we will discuss the mechanism of Ziegler-Natta polymerization. The structure of active centers in Ziegler-Natta catalyst is firmly established only for metallocene catalyst. A metallocene complex Cp2 ZrCl2 reacts with MaO and is transformed in a metallocenium ion, that is Cp2 Zr positive CH3. It is a polymer molecule, grows in length by numerous insertion reaction of C double bond C of one alkene molecules into the ZrC bond in the ion. It can be explained by this reaction Cp2 Zr plus bond CH3. This is the metallocene complex and reacting with this CH2 double bond CHR and converting in metalloselenium ion, that is Cp2 Zr positive CH2 CHR. Polymerization reactions of alkene with solid titanium based catalysts occur at special titanium centers located on the exterior of the catalyst crystallites. Some titanium atoms in these crystallites react with organo-aluminium co-catalyst with the formation of titanium carbon bonds. The polymerization reaction of alkenes occur similarly to the reactions of metallocene catalyst, which can be understood by this chemical equation. This is titanium CH2 CHR polymer. When combining this CH2 double bond CHR, then the formation of this polymer is going on. Vinyl polymers are polymers made from vinyl monomers, that is small molecules containing carbon-carbon double bonds. They make up largest family of polymers. The simplest vinyl polymer is polyethylene. Polyethylene is made from the monomer units, that is ethylene. When polymerized, the ethylene molecules are joined to form a long chain of many thousands of carbon atoms containing only single bonds between atoms. Their backbone is the extended alkane chain made by polymerizing an alkene group, that is C double bond C, into a chain which contains C single bond C. So, the monomer units of vinyl polymers are, that is polyethylene made up by monomer unit ethene or ethylene, polypropylene made up by the monomer unit propene or propylene, polybutadiene made up by the monomer unit butadiene, polystyrene is made up by the monomer unit styrene, and polyvinyl chloride is made up by polymerization of the monomer vinyl chloride unit, that is CH2 double bond CHCl, that is also known as chloroethene. So, the common examples of vinyl polymers are polystyrene, polyvinyl chloride, polypropylene and polyethylene. Now, we will discuss the condensation or step growth polymerization. It is the another type of polymerization. First, we have discussed addition polymerization, and now we will study or discuss the condensation step growth polymerization. It refers to a type of polymerization mechanism in which bifunctional or multifunctional monomers react to form first dimers, then trimers, then oligomers and eventually long chain polymers. Many naturally occurring and some synthetic polymers are produced by step growth polymerization as polyesters, polyamides, etc. Due to the nature of the polymerization mechanism, a high extent of reaction is required to achieve high molecular weight. There is also the possibility to have more than 2 reactive sites on a monomer. In this case, branched polymer are produced. We are showing through a diagram of a step growth polymerization. Single white dots represent monomers and black chains represent oligomers and polymers. In this diagram, these are the monomer units converting into dimers, then trimer and then oligomer. And finally, these trimers are converting into oligomers, and finally, the formation of step growth polymer is going on or takes place. So, here we are taking some examples of condensation polymers, that is polyesters made up by the repeating units of esters, and examples are polyethylene terephthalate, that is also known as PET, PET, polyhydroxybutyrate, that is PHB, and polybutylene terephthalate, that is PBT. These are the examples of different kinds of polyesters. Another example is polyamide, that is made up by the amide bond or amide linkage, and the examples are nylon 6,6, Kevlar and nylon 6. Another example is polyether. These are made up by the linkage, or these are made up by the ether linkage. Example polyphenyl ether, that is PPE, and polyphenylene oxide, that is PPO. Phenol formaldehyde, that is also known as bakelite. Polysulfide, that is the kind of synthetic rubber. Example is thiocol. So, the distinction between addition polymerization and condensation polymerization was introduced by Hume Carothers in 1929 and refers to the type of products respectively. The differentiation between step growth and chain growth polymerization can be understood by this chart. In step growth polymerization, no initiator required, whereas in chain growth polymerization the initiator requires. The average molecular weight increases slowly at low conversion and high extents of reaction are required to obtain high chain length, whereas in chain growth polymerization molar mass of backbone chain increases rapidly at early stage and remains approximately the same throughout the polymerization. So, viewers, in this session we have discussed about polymers and polymerization. Polymerization we have discussed is of various kinds, that is addition or chain growth polymerization. Further of following types, that is free radical vinyl polymerization, ionic vinyl polymerization, Ziegler-Natta polymerization and vinyl polymerization. Another type of polymerization was condensation or step growth polymerization. In the next session, we will discuss about polyesters, polyamides, resins as phenol formaldehyde, urea formaldehyde, epoxy, polyurethanes along with natural and synthetic rubbers. Thank you.